Hi and welcome. Today we're going to be talking about comparing two populations, and this is going to center around hypothesis testing and also confidence intervals. Okay, so I should probably add this. Okay, so again, two methods comparing two populations: independent samples or non-paired data. So for today's lecture, it's centered on comparing two populations. When we have a situation in which we can't somehow pair our data, um, and that's what's most common. So a pairing situation might occur with twins, or in which case it makes sense to compare individual observations. This is very hard because it requires equal population sample sizes, because we need to have one individual to compare with the other person in the population. And that, as I said, is very, very difficult to do. It's often the times that that's false, that we just have a random sample of a population and we want to compare it to someone with a treatment. Okay, I'll give you a quick example of this. But first, I need to just discuss with you what's the null and alternative hypotheses here. So as it says, you won't have we're not in a situation where you have paired data. Okay. The sample sizes could be different, but you'd still like to test the hypotheses and compare two populations. And by comparing two populations, I mean testing the hypotheses that the mean of population 1 is equal to the mean of population 2. And the alternative hypothesis has one of the two forms. It's either that one is greater than the other, or that one is not equal to the other. Okay. One example that we'll look at will be diets, in which we're interested if the mean of diet 1 is equal to the mean of diet 2 if they have the same weight loss, or if one has a greater yield. We could be talking about salaries between men and women, such as, do men have the same starting salary as women? Or is one greater than the other, or is one different than the other? These are the methods that allow us to answer these questions. We could be asking if the average temperature for a certain set of observations is the same as another set of observations. Okay. So we're always testing our null hypothesis, which is always equality, against one of these two forms. Okay. Now it could be that the mean of population 2 is greater than the mean of population 1, but that's just interchanging what you call population 1 with population 2, and is therefore included in this example. Okay. So when you're comparing two populations, there's certain assumptions, and it's good to know how this works. Okay. So one assumption is that the two samples of each population are a representative sample of the population. The samples are independent, meaning someone in population 1 typically doesn't affect someone in population 2. Okay? And each population has a sample size of at least 30 or more observations. Okay? So going back to independent, it's not only important that someone in population 1 doesn't affect someone in population 2, but also that someone in population 1 doesn't affect another observation in population 1. Okay, so both independent with respect to population and independent with respect to observation. Okay. So how can we assess our null hypothesis versus our alternative hypothesis? And it's with this t-statistic, which centers around the difference. The difference in observed values. The difference in observed values is the sample average x1 bar minus x2 bar. And we divide by our standard deviations of the pooled population, which is in the denominator of this t-statistic. Okay, when we're doing a hypothesis test, we see that the two means are equal and that our t-statistic is just this. Because they're equal, that term disappears. It becomes 0. Okay. Now, the degrees of freedom that you have to use in the t-distribution is a little bit more complicated than before. It's given by this formula. Okay. And I want you to just be a little bit careful. So, like, if we get, this gives us a number, and it might be like 4.67, and we round down to the degrees of freedom of 4. But if we get a value here of like 0.51, we're not going to round down to degrees of freedom of 0, because the smallest number of degrees of freedom you can have is 1. So if you get a degrees of freedom of 0.51 or 0.29, in that case, you're just going to use 1 as your degree of freedom. Okay, that's all you can do. Okay, and that here is illustrated in bold. So keep in mind, degrees of freedom has to be an integer. Typically, you round down unless it's less than 1. Then you just set it equal to 1. And it can happen that the degrees of freedom are a fraction that's less than 1. That is realistic. Okay. Now, another way to assess hypotheses, an important thing to do, is with a confidence interval. It tells you how much the estimated difference might be. It also allows you to assess a two-sided hypothesis. That is, the mean 1 is not equal to mean 2, but it's not able to assess a one-sided. That is, mean 1 is greater than mean 2. So be very careful when you're using hypotheses test what the alternative hypothesis is. Okay. So just like before, usual, the confidence interval is given by our point estimate. That is the mean estimated difference, the difference of two means, plus or minus a margin of error. That margin of error is dictated by the t-distribution and your standard error. Okay. So let's see how this works. Okay. So we've got a nutritionist who wants to know if a low-carb diet is more effective than a high-protein diet. And to test this claim at the 5% level of significance, a random sample of 50 is taken. And 25 individuals are randomly assigned to each group. We're going to assume the data in the treatment group is normally distributed, and the results of each are displayed in the table at the next slide. Now, I do just want to take a break and say that this is probably the most important material of the course and what you would use in real life. So, some of these examples are inspired by actual statistical studies, and some of them are actual statistical studies. Okay. So the very first thing we need to do is to make our statement of our null hypotheses and alternative hypotheses. Our null is always a statement of equality. So that is that the low-carb diet is equal to the high-protein diet. They have the same average weight loss. So we're comparing our two populations, those in the low-carb diet to those in the high-protein diet. The researcher here believes that the low-carb diet is more effective than the high-protein diet. So that's what the nutritionist wants to prove, and that's our alternative statement. So typically what the researcher wants to prove is our alternative hypotheses, and it has to be expressed in one of those two forms. Okay, so along with this little description, we need data, because without data, we can't assess this claim. So suppose we have data, and it turns out the sample average of the low carb is 5.5 pounds. That's how much they lose on average. And the high protein diet, they lose 4 pounds on average. Okay, sample standard deviations are going to be 5 pounds for low carb, 3 for the high protein, and the sample sizes are equal. Notice that with this design of experiment, because of the randomization, we'd be able to infer causation so long as we have a representative of the population, and because of the random samples here, and it's one of the most trusted design methods that we'd have. Okay, so let's begin by testing this hypothesis. We calculate our t-statistic, which is the observed value. The hypothesized value is 0, and we need to divide by our standard error. So the observed value, that's just the difference in means, that's 1.5 pounds. Our hypothesized value under the null is 0, as we said. Okay, and our standard error we calculate in this way. Okay, now the degrees of freedom becomes a little bit tricky, so let's calculate it. We need to calculate V1 and V2 here, then we plug it back into this formula. We get 4.62, we round down to obtain 4. Keep in mind, if this was just 0.62, in that instance we'd round up. So if it's just like 0.62 or 0.71 or 0.79, it gets a value of 1. Okay, because that's the smallest value degrees of freedom can have. Okay, so now we test this hypothesis, and this is called the p-value method. We calculate the probability t-distribution with 4 degrees of freedom is greater than its statistic, and that's here. This reduces to probability of t-distribution is greater than 1.29. And this is equal to, excuse me, this should have been 0.13, equal to 13%. And so we would fail to reject this at the 10% level of significance. Another method would be to compare the t-statistic to the critical value of 2.13. Okay, now let me show you, before I get into the critical value method, let me show you how to calculate this probability, this 13%. So we have a t-distribution with 4 degrees of freedom is greater than 1.29. That's expressed here. How you calculate this probability is you need a calculator. There's a great one online. So I'll go to it right here. If you Google online stats book, okay, it's a free online book. It has a list of calculators that you're welcome to use for this course, as you've noticed. And I'm going to go to the t-distribution. I'm going to enter in the degrees of freedom, which is 4. Then I need to remember the t-value. That's 1.29, so I plug that in for t right here. Okay. I get 0.266, which you should notice is not equal to 0.13. But what you should notice is 0.26 divided by 2 is equal to 0.13. And that's because it's a two-sided value. So 0.26 is what's the two-tailed p-value. So you need, that would only, this two-tailed p-value is for assessing the null of mean 1 is not equal to the mean of null 2. If it's a one-tailed test, you have to take this p, which is two-tailed, and divide it by 2. And that's what we did here. Okay? Now, there's another way. So you should notice I can reject this at the 10% level of significance. I can also reject it at the 5% level of significance. There's another way of doing this, which is comparing the critical value to the t-statistic. Okay, so instead of using the t-distribution calculator, I can use the inverse t-distribution. I want um, to obtain the critical value of a t-distribution with 4 degrees of freedom. So I'll put 4 here. Because the confidence level, you might say, oh, it's 5%, but it's one-sided. So I have to multiply that by 2. And I get this 2.132. Okay, and that's how I get this value. Okay, now 1.29 is the t-statistic. That is less than this 2.13, and that is why I fail to reject the null hypotheses, is because of this. Okay, so let's just emphasize that. Okay, now let's go over another example. So here we have a sociologist. They want to know, they believe that males have a higher wage than females, and to test this hypothesis, they take a random sample of 50 males and 35 females, and they find that the average hourly wage for females is $19.25 per hour with a sample standard deviation of 3. For men, it's $24.75 per hour with a standard deviation of $4 per hour. The researcher wishes to test this hypothesis at the 5% level of significance. So the first thing we're going to do is we're just going to state the null and the alternative hypotheses. The null is that the means are equal. That's always the case. So the mean wage starting salary for men is equal to the mean hourly wage for women. And the alternative is what they believe. They believe that men are earning more per hour than females. And that's encapsulated by that first sentence. So let's go through this testing procedure. We have the observed difference. That's $5.5. Okay. The hypothesis values under the null hypothesis that there's no difference, that the two populations are equal. Okay. Our standard error is given by this. Okay. Now, the more complicated thing is we need to calculate our degrees of freedom. Our degrees of freedom is 1.28. We're told to round down to 1. Keep in mind, if this was just 0.28, we'd have to select 1 because 1 is the smallest value for degrees of freedom. Okay. Okay. Now, some side calculations that were needed to calculate degrees of freedom were this V1 and V2, which is the square of the standard deviation divided by its sample size, and then we plug it into the formula for degrees of freedom. Okay. Okay. So we want to test this hypothesis, so we have a t-distribution with 1 degree of freedom. That's greater than the observed value, which is 5.5. The hypothesis value is 0. We divide by our standard error, 0.759. And we get 0.0436. That's less than 5%, so we reject the null hypothesis. This was the p-value method. Now, if you want to see how to use the p-value method, we'll need to use an online calculator. So we'll go to a t-distribution with 1 degree of freedom. Okay. I'll need to go back. So in the t-distribution, so 1 and 7 point, we need to check 23. 7.23. Calculate that. We get 0.35. Let's just double refresh this. Because the degrees of freedom is 1 and 7.23 goes there. Yeah, that. And this is 0.0875. So you're probably wondering how I got something like 4%. So 0.0875 divided by 2, that's equal to 0.0436. And that's how I get this 4.36%. That's less than 5%, so we can reject the null hypotheses. Okay. Now I could also calculate a confidence interval for the difference in starting salary. And the confidence interval has this form, the observed difference in means. So that'll be this, that'll be 5.5, plus or minus the standard error. So this is part of the standard error, and the other part comes from the t-distribution. So let me show you how to calculate this. So we know the t-distribution has 1 degree of freedom. We're looking for a 90% confidence interval. So let's go back. We'll use the inverse t-distribution right here. 1 degree of freedom. We want a 90% confidence interval. We get 6.31. Okay, and that's how I get this number 6.31 is from this calculator. Okay. Now, this calculator, it always works. You don't have to worry if it's need to divide by 2 or anything like that for confidence intervals. But for hypothesis testing, you might need to be careful about your level of confidence. Okay, and when we do that, we get 2.16 and 8.83, indicating that the average difference in hourly wage could be as little as $2.16 per hour or as much as 8.83. A whopping 8.83. I feel like I could do a lot with an extra $8.83 per hour. Okay, so just to summarize, the estimated pay difference, that's just the observed difference in averages, $5.5. 90% confidence interval says it could be as low as 2.16 or as high as 8.83. Okay, and 90% confidence interval indicates alpha is 10%. Female employees at a bank. And there were 32 males and 61 females that were hired between 1965 and 1975. The only variable I'm interested in here is BSAL. That's the annual starting salary at time of hire. And I'm also interested in sex of the employee. I have a very simple question for this data, but first let's just look at what this data looks like. Okay, so here I have starting salary, I have sex. I'm going to ignore these other variables, but I can take them into account. I just have to use regression if I'm going to do that. Okay, and we haven't learned that yet. So right now I'm just going to start with how we would compare and answer a very basic question. That is this question: do males earn more than females at this bank? And we're going to test this hypothesis at the 1% level of significance. Okay. Well, to effectively deal with this data, keep in mind, there are more observations than this, as I have precluded and alluded to, and that you need to use a statistical analysis software to effectively deal with all that data. Well, I'm going to do that for you, and here's the output. So I compare the two populations with the t-distribution, and it gives me this p-value. This p-value is 3 times 10 to the negative 7th. That e means it's 10 to the negative 7th. That's much less than 1%. Because the p-value is less than 0.01, I can reject the hypothesis of equal means, meaning I reject that the starting salary of men is equal to the starting salary of females. And this 95% confidence interval here, it tells me that the difference in starting salary could be that men make almost $1,100 more, just rounding up a little bit, more than women, or on the smaller spectrum, that they make $536 more than women on the lower end. Okay, and if I want the estimated amount by which they make more, I'm just going to subtract the female salary from the male salary. Okay. So again, really important here is that we understand p-value. Since the p-value is less than 1%, we clearly reject the null hypothesis of equal means in favor of the alternative that men make more than women. The estimated wage difference is the difference in means, $818. The confidence interval tells us how much the interval could be, how much the difference in salary could be. Okay, So both hypothesis testing and confidence intervals are really useful here. And I hope that you can see some practical application for comparing two populations, because they're used all the time to answer questions. Thank you very much for joining me.